Range. Remember the range? The largest number and the smallest number, and find the spread between them. Subtract them. And our data here, we have put it in order from smallest to largest. We found out $615 is the biggest rent we found in our sample. $425 rent was the smallest. The range, if I was asking for it, you need to show that you took the largest minus the smallest. That's the work, where the points are. That you're identifying the largest minus the smallest equals that range. So 190 in this case, 615 minus 425. Variance. Now, I found a better example than just reading this on variance. I wrote myself a note so I could show you this. So I got to remember where it's at here. Hang on. Right here. You ready? You've got some data. This is how you do variance. I know this is review for you. But you have some data, and if this was manual, if this were on the first test, and I'm asking you to just do it manually to show me that you could do the steps, maybe only 5 or 4 pieces of data. Notice the second column is using the mean of that data every time. And so, if you set up columns, you have the 5 pieces of data. You quickly show the work that you added all 5, divide by 5 to find that mean. Then, you subtract that mean from every piece of data. 3450 minus 3540, the mean. The difference is negative 90. Go to the next one. 3550 minus the same number, the mean, 3540, the difference. The next column is whatever you found for that difference, you square it. And the negative should be gone. There never should be negative numbers in that last column. That means you're making a mistake. So you're doing that for each one, subtracting the mean. Then once you get that difference, square it. And if you accidentally subtract the other way, and that second one would be negative 10, the first one would be positive 90, who cares? It doesn't matter, because once you square it, the negative's gone anyway. You can't make a mistake there. Now, you add all your squares together. And almost always in this class, you're going to be calculating a sample variance. The difference between sample and population is that with population, you would now divide by however many pieces of data you have. But almost all these questions are about samples. You have to divide by however many pieces of data you have minus 1. So in this case, we have how many here? 12. So we total all those squares together, sum of each of those total squares, each one of those added together, divided by the number of pieces of data you have minus 1. We took this formula that people look at it first and they go, oh my God, how do you get that? You break it into these columns, it makes it very easy. That whole top part is just adding all those squares together. That's all it was. Divided by however many pieces of the original data, 12 minus 1. Now, if we're doing the variance for those apartments, we would find the mean of all 70 of them. We subtract the mean from all 70 of them. Whatever the difference is, we square them, divided by what?
69.
Exactly, you got it. Because there was 70 of those in the sample of the rent. And that's the key. That's probably a big part, is showing these columns, showing that you can get the squares, showing you added the squares together, showing you're dividing by however many minus 1. That's the big part, divided by the right number. Whoop, whoop. So let's see, we have just an example? We don't. Now, the standard deviation. Go back to that example again. The standard deviation, once you have this variance, all you got to do is square root it. You square root it. The symbol for standard deviation is the same symbol as variance, but without that little square. If it has a square, it's calling it a variance. If it doesn't have a square, it's asking you for the standard deviation. You do everything the exact same. You get to this spot right here, and then square root it. You now have the standard deviation. Almost always, when we get past these first few chapters, you will be using the standard deviation instead of the variance. So you've got to know that last step. You've got to do that square root. Back here. Coefficient of variation. We get a new example here? We don't. Wow. Coefficient of variation. You take the standard deviation you calculated, the mean you calculated, and just divide. Standard deviation divided by the mean of the sample. That's why we're using the left one here, because we're almost always going to be doing it for a sample, even though it's the exact same calculation. One symbol means standard deviation of a sample. That symbol is standard deviation of a population. Like I said, this semester, focus on all the sample formulas, because almost everything's about samples. Divided by the mean of the sample, that symbol is the mean of the population. So focus on this one. You're going to get blankety blank divided by blankety blank. Well, matter of fact, here's an example. And then just turn it into a percentage. Move the decimal 2 places to the right, which is multiplied it by 100. Turn it into a percentage. So let's say we've got all 70 of those rents, and we found the variance. We took each one of 70 of them and subtracted the mean and squared that difference. We added all the squares together, and then we divided by 69, like you told me. The variance is 2,996. The standard deviation is the square root of that. 5474 is the standard deviation for those rents. You know, they vary from each other. The coefficient would be that standard deviation we just calculated, divided by, earlier we just calculated the mean of all 70 rents. It was 490.8. That will give you 0.1115. Move the decimal 2 places to the right and add the percent symbol. 11.15%. Now let me explain why this is an important calculation. There have been many times where I'm trying to evaluate if something is more efficient than something else, or has less variance in it. But they're two completely different things. They have such a different mean, they have such a different standard deviation that I'm not comparing apples to apples. So if you do this last calculation, if I take the standard deviation of this sample divided by its mean, and then I take this one, which is completely different standard deviation and mean, but I take its standard deviation divided by the mean, I turn them both into percentages that are coefficients of variations, I now can compare apples to apples. The one with the lowest percentage is varying less than the one with the big one. If this were investments I'm evaluating, and I used to do a lot of investing, I would want to go with the less risky investment. It's probably why I'm doing this coefficient of variation, to figure out which one's less risky, even though they're completely different. One's at 100 and something a share, one's at $10 per share. You know, and they're two completely different standard deviations and means. I want to be able to compare apples to apples, so I'll go with this calculation. And that allows me, now I'm in the same ballpark. It's how their individual standard deviations are compared to their individual means.
Sorry about that. Would that be like basically looking at the volatility?
The volatility is exactly what it is, which in most investing is a beta, is called. And that beta is kind of similar to this. If you ever go to Yahoo Finance and you look at a stock's beta, it's trying to tell you how much, how volatile it is compared to the overall market. If a stock has a beta of, let's say, a positive 0.5, it's less than 1. 1 beta means that that stock is going up and down just like the overall market's going up and down. Very similar roller coaster. If it's a negative 1, it means that stock is going up and down similar, but in the opposite direction of the overall market, but the same levels of ups and downs. 0.5 is less volatile. It's a positive 0.5. It goes in the same direction. If the market, overall market's going up, that stock's going up, but not as much. And same with going down. If the overall market's going down, that stock's going down, but not as much. And most investors feel that a 0.5 has less risk because it's less volatile than the overall market compared to a stock you may be looking at that has a 1.6 beta. That one's going up and down like a roller coaster, even more than the overall market. So this is about evaluating possibly like risk, like the beta does. For me, this is what I needed someone to show me when it came to statistics so I could understand this whole probability thing and the bell curve. It was like the bell curve was, I just couldn't get a handle on what it really meant. So I'm going to try to bring the bell curve overall to help to make it click for you the way I needed it to click for me. You got to look at this line at the bottom. It's basically just a number line. And the numbers change every time we have different samples. And the whatever number's in the center of this number line is whatever the mean of the data is. And those apartments, those 70 examples, I think the mean was like 492 something, right? Right around there. And if we were to do a bell curve, that would be right here, the 492. And when we calculated the standard deviation, it was like 56 or 59, I don't know if anybody has a PowerPoint in front of them. 50, somewhere around 50 something. If we were putting together a number line, we would want whatever that mean is, plus one standard deviation to be about this far away on the number line from the mean. And the second number, the other number here, would be whatever the mean is, add now another 59 and another 59, 2 standard deviations away. So if I were making a number line, it would be 490 whatever, plus 56, so now we're at 500 and something, would be right here, maybe some numbers in between, evenly apart, that makes sense. We'd add 2 standard deviations, that'd be the number here, 3 standard deviations. Now going this way on the number line, we take the mean, we would subtract now whatever the standard deviation is, 56, 59. So 492 minus 56. We want that number to line up right here, minus another 56 or 59, minus another. And now we have our number line here. Everything's proportional because there's standard deviation, exactly whatever the standard deviation is apart. And now you look at this bell curve, and if I said to you, let's pretend this is like, what, 492? So this would be 550. I don't know. And if I said to you, what's the probability? Now you're looking at the bell curve, and this bell curve represents a 100% chance. If I said to you, and I put my arm right here, going straight up like a dotted line, this bell curve were all shaded in here, 1% of 100% would be shaded to the left of my arm, 50%. What would be shaded to the right? 50%. Okay. Now, if I put my arm here, would there be more or less than 50% shaded to the left? More. You got it. More or less than 50% shaded to the right? You got it. More or less than 50% shaded to the right? More. I'm trying to trick you. More or less than 50% shaded to the left? You got it. And that's what this is all about, is figuring out what that percent is to the left or right of some number. And when we get here, this is what's happening here. You ready? On a z-chart, remember in the back or front of your old stat book, and it's in ours somewhere, all the numbers on that chart are somewhere from -3 to +3. Well, those numbers are right here. They're representing how many standard deviations away from the mean, whatever that mean is. So if I said to you, calculate the z for, hang on a minute, let's say this is 492, and that's, what I say, 540, 550? If I said to you, what is the z for 550 when the mean is 492 and the standard deviation is 50-something? You would find the difference here and divide by the standard deviation, but if it's right there at 1 standard deviation, then it's going to calculate to a z of 1. Because it will be 550 minus 492 equals 56, divided by 1 standard deviation, which is 56, equals 1. It's trying to say that 1 standard deviation above the mean. So every time you do this z calculation, your answer is always going to be between -3 and +3. And it's basically telling you how many standard deviations away the number is you're being asked about compared to the mean. So, for example, we're going off camera. Darn. I need this file. You ready? Let's say we have our number line, and right here is, I'm making something up now, 55. And our standard deviation equals 3. And I said to you, what would be your z for the number, hang on, I'm almost there, 61? Someone said it, I didn't hear it. I didn't hear what you said that. That's right. And all they're doing real quick is they're saying 61 on the number line's up here, so we know it's a positive z because numbers get bigger to the right and smaller to the left, right? 61 minus 55 is 6. Divided by the standard deviation of 3 would be 2. It's basically saying, hey, you're asking about 61. Well, on the bell curve, 61 lands about right there because it's 2 standard deviations above the mean. Now, if I said to you, approximately what percent of the observations in the sample would be less than 61 or 61 or less, I'm asking you to tell me what percent from this spot right here to the left. And every one of those charts from these stat books, or if you go online and get one of those charts, they're always giving you the percentage from any one of these spots to the left. Always. And the trick is, if the question's saying, what's the probability that the sample's going to be 61 or more, well, the z is still 2, 61 minus 55, but what I'm asking you for at right here is where it lands, 2 standard deviations above. Because I said 61 or more, you look in the back of the book, you find that, but the question's asking this, you just subtract it from 100%. It's the opposite of what you just looked up. So anytime the question is asking you for the probability of some number or less, it's right there in your back of your book. But if it's asking for the probability of some number or more, it's whatever you looked up, the opposite is the answer. So show that you're subtracting it from 100%. It's the opposite. Does this help so far? So if it didn't get the light bulb, it will. We're going to go a little z-score. I already gave you the hint on z-score. It's whatever you're being asked about minus the mean divided by the standard deviation. And if your answers are mostly between -3 and +3, there are many answers outside of -3 and +3, but they're so off the chart, they're called outliers. Most questions on tests will get you a z-score between -3 and +3, because probably the next question is, what's the percent chance, or something like that. Probably, I don't know if it'll be on the first test, but we're heading to where the z always is going to relate to what's the percent chance, what's the percent of this or percent of that. Do we have an example here? Here we go. We already calculated the mean of the 70 rents was 490.8. I said 492, right? Standard deviation, we calculated to be 54.74. I don't remember that either. I kept saying 56, I think. I don't know. But then the question might say, the mean is 490.8, the standard deviation. They may even try to trick you. The variance is blanky blank 1,000. You may have to convert that to a standard deviation. How would you do it? Square root it. Good. Calculate the z for $425. Now here's what it'll say. It'll say, if we took all 70 of these rents on pieces of paper, and we folded the piece of paper exactly the same, and we threw them all into a bucket, put the cover on it, we shake that bucket, and you reach in blindly and pull one out, what's the probability that the one you pull out is going to be $425 or less? There's no exact on z-scores probability. It's something or less or something or more. It's always going to be something less or something or more. So $425 or less. To figure that out, here's our bell curve. Right here in the center is 490.8 standard deviation. I could add, we know that one standard deviation should land right here on our number line, and one standard deviation subtract should land right here on our number line. So if I took 490.8 and I added 54.74, that would be that number. And if I added another 54.74, that'd be, I got these slides out. Here's 2. That'd be that number. 2 standard deviations, 3 standard deviations. We put our number line together. Subtract, subtract, subtract. 1 standard deviation, 2, 3. Don't rely on this drawing. This is really bad. Where does 425 land on the standard deviation? It's a negative number because it's below our mean. We subtract 490, we get a negative number. We divide by 54.74, z, negative 1.2. Now look here. Here's the first standard deviation in the negative. So 1.2 would be just slightly to the left of it. So if this is one standard deviation below, it would be like right here, just to the left. Negative 1.2. And then the question's going to say, what's the probability that the piece of paper we just got out of there is going to say $425 or less based on these 70 samples? My question for you is, if I put a straight line here, is the answer going to be less or more than 50%? Less, because to the left, I said $425 or less So it's obviously, so let your logic say, if I'm looking this up, and my answer is not below 50%, I'm doing something wrong. Because it's got to be below 50%, because I'm way down here. I'm negative 1.2. Anybody look that up real quick and give me what it says in the book? All right, let's do it together then. You ready? Is it at the front of the book or back? Front. It's in the front, cover. You ready? We have positive z's right there. This is for all those calculations that are to the right of the mean. But ours is to the left of the mean, so we're going to the negative page. Hey, come on. Come on. What am I going to do here? To the left of it. Can you see it? And we said it's negative 1.2. So the next digit after 2 is a 0, right? We got exactly negative 1.2, didn't we? And if it were like negative 1.25, we got to go across to the 5. These are always the first digit to the right and the digit to the left of the decimal. That up there is always the second digit to the right of the decimal. So if it said negative 1.25, we go all the way across to the 5, and there's our probability. But we calculated exactly negative 1.2, so we go to the 0 is the next digit. There is 11.5% chance that if we were to call any apartment down there, or we take those 70, we pull a piece of paper out, there's only about 11.5% chance that that piece of paper is going to be 400 and whatever it was. I'm going to go back. Thank you. $425 or less. What's the probability that that piece of paper we just drew out is going to say $425 or more? Yeah, that's right. The opposite of the 11-point-something%, because I said or more, which is going to be the 88 whatever it is, point whatever, 11.5% from 100% to 88.5%. There's an 88.5% that the data is going to be larger than $425, and that's how Z works. I'm really emphasizing this because this is the part that's leading us to sampling research, and it's all about comparing the Z scores to different things. It all makes sense. This is all building up. I want you to look at what you see right now is the Z score for every one of those 70 rents in the sample, and they're in ascending order. We took that lowest rent out of our 70 and we subtract it from the mean and divide by the standard deviation, we get a negative 1.2. Happens to be the one we just did. The largest one, the largest sample rent that we got out of those 70, minus the mean divided by the standard deviation, is 2.27. The reason this is important is because in real research, that if you have these couple of data that for some reason the Z-score is off the chart. And we used to always say -3 and +3. Sometimes we go to 4, depending on the data. But if any of this data ends up being 4 standard deviations above or 4 standard deviations below, something went wrong, most likely. It's so far off, it's such an outlier. This is how you identify outliers. It's called an outlier. And in most research, you have to almost assume that maybe a mistake was made and you take that piece of data and throw it out. And said, we're not even going to use it. It's way out there in boonies. Maybe something happened. We're just going to use, let's say, these 69 pieces of data instead, because that's off the charts and it doesn't make sense. Maybe we accidentally, whoever collected that piece of data may have made a mistake.